Hello, I'm David Abrahams. I'm the director of the Isaac Newton Institute for Mathematical Sciences, and I'm the warm-up man for the warm-up man. I just wanted to say hello to everyone and welcome here, whether you're here as part of the programs that are going on here or as a visitor who's come to see the lecture. But it's always a pleasure to sit in on the Rothschild lectures. The Rothschild Distinguished Visiting Fellows give the Rothschild lectures for each program. They think they're treated as VIPs, but they're usually given the onerous task of giving 1 million talks in a couple of weeks. So they have the hard work, which we're very grateful for, but they're usually in very heavy demand. And I'd just like to say, welcome here. I think there is a drinks reception afterwards. And I'll pass to Chris Skinner and thank our Rothschild Distinguishing Visiting Fellow. I hope you enjoy it, and I look forward to your talk. Thank you.
So, thanks very much, David. I'm Chris Skinner, the second warm-up person, the co-organizer of the Data Linkage and Anonymisation program, on which Cynthia is the Distinguished Visiting Rothschild Fellow. And it's good to see people from a number of the different programs here today. So I won't be saying very much, but I'm delighted to introduce Cynthia. She's currently Distinguished Scientist at Microsoft Research, but in transition from January next year, she's going to be Gordon Mackay Professor of Computer Science at Harvard University. She had many honors, member of the National Academy of Sciences. I'm not going to list the others. Her work is very wide-ranging, but of particular relevance today is the huge influence she's had in demonstrating how the mathematical sciences can contribute to the science of data privacy and the sort of key role that has in the modern data revolution, data science. And in particular, in just the last 10 years, in the field of differential privacy, the topic of tonight, in which she has been a pioneer, it's seen a real remarkable expansion of research and literature. So I think we're going to hear a bit more about that today. So really pleased to have you so much here, Cynthia. Over to you.
Okay. Just connecting myself here. So, good afternoon. Thank you very much for inviting me as the fellow, and thank you for the introduction, and thank you for coming to this lecture. So my interest in privacy in the modern world arose from conversations with the philosopher Helen Nissenbaum. Nissenbaum studies philosophical issues that arise in the context of new technologies, and she was puzzling over what does it mean to have privacy in public when there are surveillance cameras everywhere. And eventually she developed a theory called the theory of contextual integrity, which has had a very big impact on the field. But as a result of these conversations, I wanted to do something that had to do with privacy, and I looked for a piece of the general privacy puzzle that I could sink my teeth into, and settled on privacy-preserving data analysis. So here I am giving a lecture, and some of my slides, including this one, were given to me by Kobi Nissim, one of the co-inventors of differential privacy. Now, Kobi has generously given me all of his slides, and striving to develop a better lecture. At some point, I ask you, how many of you prefer Kobi's slides to my slides? So given the context, you might think that this is sensitive information. And so somebody in the audience suggests that we should use the cryptographic primitive or tools of secure multi-party computation. This is a miracle of modern science, truly, that allows us to cooperatively compute the value of some function on our pooled data without leaking any more information other than the actual outcome the value of the function. Nothing else gets leaked. So you all have your opinions. We run the protocol, and somebody tweets the results. And then Helen stops reading her email and kind of looks up and says, hey, what's going on? So we explain to her the survey that we're doing and why we're doing it, and she says, yeah, I'd like to contribute to this survey too. So we run the calculation again. Now, somebody tweets the results there too, and I learned that 14 people prefer Kobe's slides. And there are, of course, 100 of you in the room, so you figure that Helen prefers Kobe's slides with probability about 14 over 100. But there was that previous outcome, and I have access to that too. And now we've compromised Helen's preferences. So secure multi-party computation is a tremendous tool, but it doesn't solve the privacy problem for privacy-preserving statistical data analysis. And if you're familiar with homomorphic encryption, same deal. It's the same kind of problem. So, what is the problem of privacy-preserving data analysis? So we have some data. We want to run an analysis on it, and we want to learn the outcome. And the data may be distributed and it may be encrypted, but this is our basic problem. And the data set has some personal information. Maybe it's health information, maybe it's some social networking information that people would like to keep private, and so on. And so the problem is, how do we compute and release functions of this data set for, say, academic research or informing policy decisions and allocations of funds, national security questions, and so on? How can we do all of this while protecting individual privacy? So that's the problem that I bit off from these conversations with Nissenbaum. Now, of course, this is not a new question. And you've probably all heard of de-identification and anonymization, even in the name of this program, although I argued with Chris. And what is de-identification? De-identification is where you start with a database, and you run the database through some sort of sanitizing mechanism, M. And maybe it redacts some fields and throws away some outliers and things like that. And it produces a putatively sanitized data set, which is represented by that thing in yellow. And the idea is that the analyst can now just have at it. She gets total unfettered access to the sanitized data, and she can study it to her heart's content. Now, the only thing I'm going to say about this today is that a host of results show us that de-identified data isn't. Either it is not de-identified, or it is no longer data. And that's a separate topic. I should mention that the President's Council of Advisors on Science and Technology, in their report on privacy technologies in May of 2014, had some very nice language in which they explain that de-identification fails for the same reason that big data is so effective in general. Okay, so if we can't release de-identified data, if we abandon that direction, then maybe we can say, yes, my analyst can interact with the data set and she should only receive statistics. What can we do in this setting? And this actually gives me the opportunity to formalize my model of privacy-preserving data analysis. So here I have the analyst on the right, and she asks a query, Q1, and she gets an answer, A1. And depending on that answer, she chooses a next query, Q2. Q2 does not have to be fixed in advance. This can be adaptive. And based on the answer to Q2, she may decide to drill down further a particular way, and that will inform her choice of Q3 and so on. And maybe what she wants is some synthetic data. And so Q1 might be, please give me a synthetic table, a table of synthetic data that shows correctly the relationship between attribute 1 and attribute 6. Or maybe her query is, give me 5 statistics of the following form, I don't know, a median, interquartile range, and so on. Okay, so as we saw in the very, very first part of this talk, the fact that something is a statistic doesn't mean that it's actually giving you privacy. And that's a little bit counterintuitive, and that's why we started with that example. Maybe, so what our intuition about a statistic is it's representing the population as a whole, and if one person is in versus out, it doesn't really change the outcome. It doesn't really change the conclusion that you draw about your population. And yet we saw that a couple of adversarial statistical queries could be problematic. There's another kind of an attack, which I will say more on the next slide. But basically, it allows the determining of the presence of an individual's genomic data in a forensic mix. A really important result in formulating this field is the so-called reconstruction or denonisme or Big Bang attack, which says the following. Suppose you have a database, like a medical database, and there are a number of not sensitive attributes that can be used to name people. But there are sensitive attributes in the data set. For example, whether or not somebody has a history of depression. And what these attacks allow you to do is to deduce from approximate counts of the number of depressed individuals in several large and overlapping data sets, almost completely correctly reconstruct the depression bit column, which has got to be a privacy violation under any definition of privacy, but it kind of gives us a baseline. Okay. Now, in this attack, I like to call it a needle in a haystack. The ingredients of the attack, actually wait, before I give you the ingredients, suppose for simplicity that we were all single-strand DNA individuals. Now, take any two people in this room, their DNA agrees in most of the locations, but there are a few locations where there is variation, large variation among the population. And those locations are called SNPs, for single nucleotide polymorphisms. So for example, in one SNP, maybe 97% of the population has a C and 3% has a T. And in a genome-wide association study, a very simple thing that is done is to look at these various SNPs and to look at the relative counts or the allele frequencies in a case group of people who have been diagnosed with an illness and a control group, looking for SNPs that seem to be associated with the illness. So, the ingredients of this attack are pretty simple. SNP statistics, allele frequency statistics, for the case group and the control group, and the DNA of a target individual. Now, it's very easy to get someone's DNA. We shed DNA wherever we go. And so this is an attack that actually could be launched. And the attack measures whether the target DNA is closer to the case group or that of the control group. And we're using here the fact that there are many, many measurements in the genome-wide association study. So Homer et al., who devised this attack, were, at that time, the technology was giving tens of thousands of SNP allele frequencies. Now they give 1 million or 2. Okay? So there is no, all that's being released here, all that's being released is a bunch of numbers. This is a statistical attack in sort of its purest form. And you can see from this attack that we are really in a post-P PII era. So PII stands for personally identifiable information. You see that term all over the place whenever anybody is doing anything with real data sets, at least in industry. It is, in the words of Mark Rotenberg, the founder of EPIC, the Electronic Privacy Information Center, all of modern privacy law is centered around the notion of PII. And this example shows that as we sort of colloquially understand the expression PII, it is the wrong lens through which to think about privacy in the context of statistical data analysis. Okay, so data privacy, this is a problem that's been studied, statistical privacy. It's a problem that's been studied at least since the 60s. There are a lot of approaches, the identification, redaction, cell suppression, swapping, synthetic data sets. And these techniques are typically either syntactic rather than semantic, or they are thwarted by some very specific, sorry, I wrote the wrong thing. They are designed to thwart very specific attacks, but not all attacks. And the attacks started coming. So there were the re-identification attacks of Sweeney, reconstruction attacks, the Big Bang attacks that I mentioned earlier. There were attacks on auditors. There was the AOL debacle. There was the Homer et al. Genome-wide association attacks, the privacy attack on the Netflix prize data, social network, anonymizations, and so on and so forth. And in general, these just didn't work. Now, these results also can be viewed as a sort of fundamental law of information recovery that say that overly accurate estimates of too many aggregate statistics will destroy privacy. So what the fundamental law tells us is that there is going to be a limit. No matter how fabulous your technology is, there is going to be a limit on what you can do with it. Okay. So there are two kinds of problems that come up. One of them is just the computational ability to do the reconstruction, and the other is just access to all kinds of extra information that can be brought in to help launch an attack. And when she was CTO of the Federal Trade Commission, LaTanya Sweeney said, computer science got us into this mess. Can computer science get us out of it? So let's try. First of all, we have to come up with a definition of privacy, one that is amenable to mathematically rigorous formulation. So here I have a data set, my analyst, and let's say Nissenbaum is in the data set. And the question is, what kind of guarantee of promise would we like to make to Nissenbaum? So one possibility is to say that the data analyst can't learn anything new about Nissenbaum as a result of interacting with the data set that she didn't know before interacting with the data set. And this was a desideratum that was articulated in 1977 by the statistician Tordelinius. It's also very natural if you're a cryptographer because it is extremely close in spirit to the definition of semantic security for a cryptosystem. So, coming from cryptography, this is exactly where I started. But the problem is that if that's your definition, then what is the point of your data set? So let's go into that in a little more detail. Let's assume that I'm from Mars, and I incorrectly believe that all humans have 2 left feet. And in particular, I believe that Nissenbaum has 2 left feet. And I interact with the data set, and I learn that almost all humans have 1 left foot and 1 right foot. So now my view of Nissenbaum, my understanding of her, has changed. I've actually learned something about her. I've learned that she doesn't have 2 left feet, almost surely, and she probably has 1 left and 1 right. So now we ask the question, did I compromise her privacy? Did this system compromise her privacy? Do you have an opinion? Do you need to go through secure multi-party computation to tell me? Do you think this is a privacy compromise or not?
No, because it's a common characteristic of everybody. So it's not, not identifying her as an individual particularly.
Okay. We'll get back to that.
You haven't defined privacy yet.
No, but what is your gut feeling about this? Is it bad or is it good? Is it okay? Is it not okay?
My gut feeling is that it's okay, but according to the 77 definition, we've compromised our privacy.
That's true, but maybe you don't agree with the 77 definition. Maybe you think that it's too restrictive. So there's no right or wrong here. It's just a question of opinion. Now, we took the opinion that it was not a privacy compromise. One could perhaps argue otherwise. But we decided that we were not going to call it a privacy compromise. And the intuition, for our perspective, is very much like Jane's, is that ideally we would have learned the same things about Nissenbaum even if she had been replaced in the data set by another random human being. And that's a sort of stability notion. It says if you perturb the data set a little bit, swap out this individual, put in another or two, you'll still learn the same things with more or less the same probabilities. And so that brings us to the English language definition of differential privacy, which says that the outcome of any analysis should be essentially equally likely, independent of whether any individual joins or refrains from joining the data set. So we should get the same outcomes with essentially the same probabilities if Nissenbaum goes away, if Sweeney joins, if Nissenbaum is replaced by Sweeney, and so on. So another way of looking at it is, here's the real world on top. There's a data set, there's an analysis, which is a computation, and it produces an outcome. And in my personal ideal world, this whole computation would be run without me, because I don't want to lose my privacy. And I'd still get to learn the outcome. And what differential privacy says is that, in some sense, these two outcomes in the real world and in my ideal world will be the same. There will be the same, similar probability distributions on outcomes. Now, before we go much farther, I just want to give you a little bit of intuition as to why we might be able to achieve such a strong definition of privacy and not totally destroy utility, because we are interested in the data analysis part as well. And just again, this is just a piece of intuition. It's not a theorem exactly. I mean, I'm not telling you a formal statement yet. Stability, we saw that it preserves Nissenbaum's privacy. It's also essential for preventing overfitting in data analysis. So there are results from the machine learning community that talk about how important stability is. So the ability to learn from your data and to generalize to the underlying distribution is actually aligned with privacy. We always think about privacy and utility being at loggerheads, but there is some sense in which, with this definition of privacy, the two notions are actually aligned. So now we're ready to give the formal definition of differential privacy. And to do this, I need to tell you about a few concepts. So the first concept is that of a pair of adjacent data sets, or data sets that differ in the data of just one person. So we've been looking at those. The data set of everybody in this room and the data set of everybody in this room plus Nissenbaum are a pair of adjacent data sets. One is contained in the other, and the larger data set has the data of just one more person. So they differ in the data of just one person. Another thing that we have to point out is that our algorithms are going to be randomized. That is, the algorithm itself will flip coins. And whenever I talk about a probability space, I'm always talking about the space is over the coin tosses of the algorithm, not over the choice of the data set. At least not until perhaps the very end of this talk if we get to another topic. So the randomness is introduced by the algorithm. And that's good because the algorithm is designed by the good guys. It's the analyst who's the bad guy. And finally, the definition of differential privacy is equipped with a parameter, which is usually called epsilon. And you can think of it as a measure of privacy loss. So a smaller epsilon is better privacy. There's less privacy loss. And it's always going to be, no, never mind. Okay, fine. So given now the notion of a pair of data sets, yes?
I'm just trying to understand this. And if you want epsilon to be small, then does the order of the data sets X and Y matter? Because if you start swapping that round.
Well, actually, what it says is for all pairs of data sets, so you can swap the roles of X and Y, and the same statement has to be satisfied. So what we get are that the ratio, well, let me say what's in the equation, and then we'll talk about it, okay? So what's the requirement? The requirement says that for any event S, that is any subset of the possible outputs, the probability that we observe S when the database is X is almost the same as the probability that we observe S when the database is Y. So if we were to divide through by this term, we would get that the ratio of this probability to this one is bounded by e to the epsilon. If we then switch the roles of X and Y, we would get that this guy divided by that is also bounded by e to the epsilon. So the ratio is between e to the minus epsilon and e to the plus epsilon. Okay? All right. So again, notice that when epsilon is 0, this just says that they're the same. That corresponds to no privacy loss. And it gives you absolutely no ability to distinguish which of the two databases are involved. Notice that this definition does not care what the analyst knows now or even in the future. Even if the analyst knows all of X and all of Y, she still doesn't know which of the two databases is actually being used just by observing the outcome. That's not enough to tell her. And as long as, and this guarantee, again, it's a guarantee that is made by the algorithm. And so it will hold no matter what anybody learns or how anybody thinks about things after the effect, after the release of the M of X or M of Y. We'll come back to those points. Now, just in case you weren't sure, e to the epsilon when epsilon is small is about 1 plus epsilon, and this can sometimes be easier for people to think about. So it's just a restatement when epsilon is small. So what is the promise that's made by differential privacy? It says that if a bad event is very unlikely when I'm not in a data set, let's say that that's the data set Y that doesn't include me, then it will still be very unlikely when I am in the data set. So what is a bad event from my point of view? Well, what if this is a data set that is some kind of power consumption data, which is a real issue, and there are real data sets of this now that we have smart grid technology in California. So a bad event might be that the police looking at that decide to bust me on suspicion of growing marijuana. That would be a bad event from my point of view. And what this says is if the police are unlikely to bust me when I'm not in the data set, they're unlikely to bust me when I am. Another possibility is maybe this is a data set of health data. And the data set teaches us that smoking causes cancer, and as a result, the smoker's premium rises. Health insurance premium rises. Okay? So what this says is you'll be no more likely to experience this rise by allowing your data to be used in the analysis than if you did not allow your data to be used in the analysis. Another thing that could happen is that I could be identified as a member of the case group in a genome-wide association study. If I'm very unlikely to be identified as a member of the case group when my data aren't used in the study, then I will be unlikely to be so identified if I allow my data to be used. And here, Epsilon, again, is our measure of privacy loss.
Okay.
Yeah.
So in let's say you're a marijuana grower. M then is a map from data sets to
Right.
police bust versus the police don't bust.
Well, M produces outputs. For example, maybe by zip code, something about consumption rates. The police look at those, and in what I would call a post-processing phase, the police decide where they're going to investigate. So,
right, it's that post-processing phase that concerns me in trying to understand this. Because if you're not in the data set and they're going to bust someone in the data set, then your little example doesn't make sense because there's no map to busting you.
The point is that they shouldn't actually know who is or who isn't in the data set. And also by one more application of this, they can't really tell the difference between somebody who consumes a lot and someone who consumes a little, even if they know that person is in the data set. Okay. Now, let's go back to the smoking example. What differential privacy does is it disentangles what you learn from the teachings of the database to what is learned from somebody's participation. Or rather, it disentangles the harms that can come from the teachings and the harms that could come from allowing your data to be used. So, going back to the smoker suffers the harm of a rise in insurance premiums either way, whether she allows her data to be used in the study or whether she refuses to have her data be used. Now, what that says is there is a way in which we could say that the teachings themselves can be harmful. And differential privacy does not address that. I mean, similarly, machine learning can be harmful. If you analyze data sets and you learn things that are not obvious correlates that you didn't know before, this could be considered harmful. Nonetheless, we are distinguishing that kind of harm from a privacy compromise. Now, especially in the case of learning that smoking causes cancer, our feeling was that this is exactly the kind of thing you want to use a statistical database to find out. Because now the smoker, for example, could decide, oh yes, I should join a smoking cessation program. There are benefits also that come from this knowledge. Okay. But she would suffer these harms and benefits sort of equally whether she participates or decides not to participate. So there are certain properties that follow directly from the definition of differential privacy, completely independent of their implementation. So we've already alluded to this a few times, differentially private mechanisms are future-proof. That if a mechanism is differentially private, it is differentially private no matter what the analyst and adversary knows from other sources, now or in the future. And it also remains differentially private even under post-processing. It also automatically, with no effort, gives gives group privacy, meaning that if you have an algorithm that is epsilon differentially private, then for your family of size 4, it is 4 epsilon differentially private for your entire family. That is, up to this 4 epsilon privacy loss, you get the same results whether your entire family is in or out. Of course, as the number k grows larger and larger, this is a serious deterioration. But that's also right, because if you change your data set a lot and say replace, a quarter of the men with women, now you have different statistics, and your data set should reflect that. Your interaction with your data set should reflect that. So you want to sort of see big changes in the signal and obscure small changes in the signal. The most powerful aspect of differential privacy is that we can understand its behavior under composition, which is what happens when you take multiple differentially private measurements of something. So we can bound the cumulative privacy loss over multiple analyses. And in the worst case, the epsilons add up. So if you do an epsilon differentially private analysis and later do another epsilon differentially private analysis, then in toto, everything you've done together is 2 epsilon differentially private at worst. Now, this is important for 2 reasons. One reason is nobody gathers a large data set and does just one calculation. It's just not what happens. Another reason, though, and in some sense this is what makes the whole topic really interesting, is that it means that differential privacy is programmable in the following sense. Think about ordinary algorithm design where privacy is not at all an issue. Anything that you can compute with addition and multiplication. But that's not how programmers operate. They build subroutines and they use library routines and so on, and they combine various programming primitives in inventive and creative ways in order to carry out some complicated computational task while minimizing the consumption of certain resources. They strive to minimize the time or perhaps the space used. And it's similar in differential privacy. We can design a few different differentially private computational primitives, and then from there we can start building more complex algorithms to carry out more complex tasks. Now, not just minimizing perhaps time and space, but also privacy loss and also utility loss. But the composition theorems tell us how we can put things together to create privacy-preserving complex analyses. So, from there, let's look at one very general but very simple differentially private primitive, which is noise addition. So let's suppose that I want to compute f of x. My database is x, which is illustrated by these sort of bluish points, grayish points on the real line. And f of x is some real valued function indicated by that star. That's the value f of x. Now, differential privacy requires that if we go to a neighboring data set y, we shouldn't really be able to tell by the output that's produced whether the data set is X or Y, because it has to have similar behavior on neighboring data sets. So here I've added one more point, that's the yellow point, and the new value of the function is f of y, which is the yellow star there. And what we're going to do in the noise addition approach is we're going to add some random noise that should obscure the difference between f of x and f of y. So for example, this may be the probability distribution on outputs when the database is x. So you can see it's kind of concentrated around f of x and it's got some tails. And maybe this is the distribution when the data set is y. So it is concentrated around f of y and it has some tails. And what we need is that if we look at for any particular possible output, let's say this point on the line, and we look at the ratio of this probability and that probability, that should be within the bounds of e to the minus epsilon and e to the plus epsilon. That's what differential privacy would require. So these distributions can't be too peaked because there would be big gaps as you got away. So how fat do these things have to be? Well, they have to be fat enough and have basically a large enough standard deviation to cover the distance between f of x and f of y. So if we call the sensitivity of f, which is denoted delta f, if we define that to be the maximum over all neighboring data sets that differ in the data of just one person, of the value of f of x minus f of y, so the worst possible change in values, then what this theorem says informally is that to achieve epsilon differential privacy, it is sufficient to add noise that is scaled to, meaning its standard deviation is something like the sensitivity divided by epsilon. So notice, the sensitivity is a property of the function, not the data set. And epsilon is our parameter, again, independent of the data set. So let's just first check that things are in the right places. If my data could radically affect the value of the function, then delta f is a large number. And we have to add fat noise. So we're going to have to add noise that is scaled to a large value if delta f is large, if one person's data can swing the value of the function a lot. And so there is delta f in the numerator. Good. Bigger delta f, bigger noise. Now, privacy, a smaller epsilon is better privacy. So if I wanted no privacy loss at all, epsilon would be 0, my ratio would be infinite, and I would have to just pick a random number on the real line if that made any sense whatsoever. There are ways of dealing with that. Okay, but if but as I increase epsilon, allow for more privacy loss, I can have more and more of a peak in my distribution, and the distribution doesn't have to be quite so fat. So there is epsilon in the denominator where it belongs. So at least the pieces are in the right places. And again, the noise depends on f and epsilon and not on the data sets at all. So that means these can be public. That is, the method can be completely public, and that also helps the statisticians to reverse engineer what's going on, to understand things about what their measurements mean. And it also lets you get sort of confidence intervals because you understand something about how the answers get spread around the true value. And we'll actually see a proof of this in a moment, but the right distribution turns out to be the Laplace distribution, and this is the parameter b for our Laplace distribution. And the standard deviation is roughly b. It's square root of 2 times b. Okay. Now, what about vector-valued functions? Well, it turns out that if you just redefine the sensitivity now in a very natural way, using the one norm, the same thing works. That is to say, if we add noise that is scaled to the sensitivity now divided by epsilon in each of the coordinates. Sensitivity is bigger now because we're capturing what's going on in different coordinates. But if we add this in each of the coordinates, then we'll remain differentially private. And in fact, the same thing is true if we wanted to ask about k different measurements, different kinds of statistics. Again, we need the L1 norm on the worst case of G1 of x, G2 of x, Gk of x minus G1 of y, G2 of y, Gk of y. Now, this is a really interesting theorem. And something just happened. So what happened? If I have, let's think about our favorite class of queries. And one thing you can ask me later in the question time is, why do we love this class of queries so much? Counting queries. Counting queries are queries of the form, how many people in the data set satisfy property P? Okay, over 6 feet tall, like muffin tops, things like that. So suppose I have 100 queries. I'm asking for each of the following 100 hobbies, how many people enjoy this hobby? How many people in the data set enjoy this hobby? So my hobbies are fishing, boating, skiing, reading, and so on and so forth. Now, the sensitivity of that query is 100. You take somebody who loves all 100 hobbies and you plot them in the data set, and you've changed every single answer by 1, and there are 100 of them. And so the L1 norm of this change is 100. So you would have to add noise that was scaled to 100 over epsilon in each of the coordinates. But suppose instead we ask a histogram query. So a histogram query says, for each of the following names, this is an example, how many people have this as a first name? So in general, a histogram is just a partitioning of the universe, and each person can live in at most one cell. And each person can change the count of that one cell by at most 1. Everybody has at most one first name. So this isn't really 100 queries, it's really one query, and its sensitivity is 1. Adding one person can only change one count, and that one by only 1. All the other ones will be 0 for the change. So when Adam Smith pointed this out to me, that's when I realized we really, like, something interesting was really going on. Okay, so here's our one theorem for the day. Why does this work? Well, so here's the theorem. If we want to achieve epsilon differential privacy, it suffices to add noise that's distributed according to the Laplace of the sensitivity over epsilon in each of the k different coordinates. So just to see, this is the probability density function for the magnitude, for the noise. This is what I'm drawing my noise in each of the coordinates. Okay. Now, let's take an output t. What is the probability that we see this? It's going to be exponential in the one norm of t minus f of x divided by some stuff. What about if the database is y? Well, this is a shorter distance because this starts here at f of y, and that's our distance. So this distance is, this is t minus f of y. So it's exponential in t minus f of y over 2 times the standard deviation, 2 times the parameter. now, our parameter is delta F over epsilon, sorry. So there's this is our ratio. This thing is bounded by the triangle inequality, f of x minus f of y, which in turn is bounded by delta F over epsilon. And so we're dividing through by delta F here, we've got a delta F over there, the epsilon comes up, and we get e to the epsilon. So we see that we have this bounded ratio condition. So let's have a little discussion about what this theorem can mean. What does it mean, say, for the genome-wide association study problem? What it says is that you can get something that has even a hope of being meaningful if we only ask on a data set of size n about asymptotically fewer than n SNPs. But if we had to scale, because we have to scale the noise somehow to the number of questions that we're asking, when we get up to n queries, the noise that we're adding is on the order of the size of the database. We're completely getting nonsense. And we get meaningless answers. So this technique that I've told you about will take you somewhere up towards n, but it won't get you past n. It won't even get you to n. But we can do better, at least if we relax the definition. And that relaxed definition that you may have heard of is called epsilon delta differential privacy. And it allows for some small probability of failing to satisfy the bounded ratio condition. And very intuitively, the reason we can do better is that when I run an epsilon differentially private algorithm, while epsilon is the upper bound on privacy loss, it is not the expected privacy loss. The expected privacy loss is quite a bit smaller. It's at epsilon squared. So the expected loss is small. And then we can do some analysis to show that it is concentrated around its expectation. And this shows us that the privacy loss random variable has sub-Gaussian tails. And that is what allows us to do better using what was called the advanced composition theorem. Now, in fact, we can take this idea of having a sub-Gaussian privacy loss as our definition, and that leads to something called concentrated differential privacy that Guy Rothblum and I started studying, but also Mark Bunn and Thomas Steinke have done beautiful work in that. They're here in the audience. And that's a very interesting and relatively new notion. It does rule out a certain important class of differentially private algorithms called proposed test release, which we don't have time to go into. But it will also let us handle close to n squared marginals, matching the negative results. So with this approach, we can get as good as anything that makes any sense at all can get for at least the counting queries. That means if somebody comes to you and says, I have a new notion of privacy and it gives much better accuracy than differential privacy, then it will compromise privacy on the counting queries if you ask this many counting queries. So keep that in mind. Caveat emptor. Once we relax the definition, we can also use Gaussian noise instead of Laplace noise, and that's very nice for a number of reasons. If the dimension of the data, so in the genome-wide association study, the dimension of the data is very large. Each person has many, many, many measurements done. If the dimension of the data is much smaller, then we can actually answer, not efficiently, but we can actually answer exponentially many queries using completely different techniques than anything that I've discussed here. Okay. One of the consequences of this is that it may be necessary to rethink your data usage. So let's suppose you really are trying to do this genome-wide association study. And the way you would do it if privacy were not a concern is you would just compute all of these allele frequencies and you'd publish them and everybody could look and see what was happening. But of course, nobody really cares about most of them. What you want to know are the interesting ones, the significant ones. So what you might choose to do is some kind of false discovery rate control where you only end up reporting a couple of significant SNPs. So that rethinking of data usage boils down often to just sort of not telling everything you figured out, but being really judicious about how you do things. And here's one example of if you want to switch to using some sort of FDR control, then you need a differentially private version of it. I did want to mention that I will be giving a talk tomorrow on the advanced composition theorem. So in particular, this question of whether we can do better or add less noise, all of this stuff, this is what I'm going to be discussing there. And my host is in the back of the room, Kayla. And good, okay. So there is a very rich algorithmic literature. And these are some of the kinds of things that people have analyzed. And there's also a book that Aaron Roth and I wrote on the algorithmic foundations of differential privacy. So today there's a theory and a practice. And the theory is mature and rich, and it has very interesting connections to a lot of areas of study that are not just privacy. It's also very interesting. So differential privacy is just now beginning to be deployed on a global scale. So the first real-world application was in the U.S. Census Bureau work on the map. I'm trying to remember the year. Anybody here know? It could be. I'm sorry, I'm just not sure. Google started using it in Rapport, which is something for locating websites that are vectors of malware in the Chrome browser. There's some interesting uses in urban mobility, and quite notably, Apple has now started to deploy differential privacy in iOS 10, so in all the iPhones and iPads and so on. And there are a lot of research projects inside industry and academia. Again, differential privacy is not a panacea. We can't do everything. The fundamental law is a fundamental law, and it can't be circumvented any more easily than you could circumvent the laws of physics. It's just math. I thought I would mention there are people who are currently using differential privacy or building pilot projects or exploring things. And I just wanted to mention a couple of reasons why they've chosen to use it. First of all, it gives them, and one strong reason has been when it gives them access to data they would not otherwise have access to. So Chrome had some very strong privacy promises about how they were going to use data. They realized they had a technical problem. It involved malware, and they needed to do something about it. And they could either change their privacy policy, which might have been something they didn't want to do given how much fuss they made about their privacy policy, or they could use differential privacy and interpret that as complying with their existing privacy policy. Others is retrofitting. There are some places where people were using various kinds of techniques, including de-identification, and they're investigating or have decided to just retrofit and use something that gave better privacy because it gives better privacy. In the case of there's a power company in Southern California that's exploring that's building a pilot implementation of a reporting tool, which So when California decided to have smart grid, they decided that they would give access to researchers, and they also decided that companies would have to report certain kinds of aggregate statistics about power consumption use. And there were a really interesting series of hearings with an administrative law judge who had a degree in math, and so it was very nice to talk with him. But in the end, some of the reporting requirements were a bit cookie cutter and a bit problematic from the privacy point of view. So there's this one company that said, you know, it's going to be difficult for us to figure out every quarter how we are supposed to do the various subdivisions in order to be consistent with what the judge has mandated. So what they are doing is they're building this pilot, and they will go back to the judge and they will ask the judge, can they use this instead? So this is very interesting, and you know, I'm optimistic. But another reason that they want to do this is that the law also requires them to answer questions from various people who want access to the data, research access to the data. Some of those people are just given free access to the data, like researchers at Berkeley, for example. The judge said they can just have access to the data. But other people who are, for example, interested in advertising insulation products to homes where they think that maybe the home is not well insulated based on the power consumption in this neighborhood. Remember that neighborhoods often were developed by the same builder, so they get a lot of information from this. So it's expensive for them to given a query, figure out how they can answer it safely. And so they want to use differential privacy for that too. And another place that that's very interested is the US Census Bureau. And John Abau describes this in part as a response to a shift in computational power and access to resources. That it used to be, he says, that most of the power was inside the census, and now most of the power is outside, and people can launch many of those attacks that we talked about earlier. So, differential privacy blurs the analyst's view of the data set. And so this provides privacy, but it may also provide a better view of the underlying distribution from which the data were drawn because of the stability properties that we talked about earlier. And I don't have time to go into it. I see that I'm over. Recent work shows that differentially private access to data will prevent overfitting even under adaptive or exploratory data analysis, which is often described as a crisis in science. And that's joint work with Feldman, Hart, Panacea, and Reingold and Roth. So let me skip to the conclusion. Privacy-preserving data analysis is a problem that has a very rich history. Differential privacy is a general solution concept, and it's robust to the networked world. There is no competing theory of privacy-preserving data analysis at this time. There are also jobs. The Census Bureau is hiring in differential privacy. Apple is hiring in differential privacy. Microsoft is hiring in differential privacy. The approach also tells us something fundamental about computing with stability and gives us a method of maintaining validity under adaptive data analysis. So thank you for your attention.
Thank you very much indeed. That was wonderful. Questions? Jane, maybe first.
Thank you, fascinating talk. I very much like the idea of preventing overfitting, It's one of these things that sounds very nice, and then one has to say, what's the definition of overfitting? What's the definition of preventing?
So one way of thinking about overfitting is, you know, we have this interaction between the analyst and the data set. Now, let's suppose that the analyst, again, let's think about counting queries. Suppose that the analyst has in mind a question. How many people in the population, what fraction of the population is over 6 feet tall? So you know that if you gather a data set, the fraction of people in the data set that you gather, using proper sampling technology, right? You gather a data set, you know that the data set will somehow be representative of the population with very high probability because it was chosen independent of the question, right? So now we're going to let the analyst interact with the data set and ask a second question and a third question in an adaptive fashion. So preventing overfitting means that you prevent the analyst from finding a query on which the data set is not representative of the population. And intuitively, if she manages to find a query on which it is not representative, she's learned something about the data. Because when she didn't have access to the data at all, in fact, it hadn't even been drawn, the probability of having that happen is extremely low. Yes? Oh.
Unless I missed it, you only danced around a definition of utility?
So I did not emphasize it, but I did mention that when you know the probability distribution, you get confidence intervals.
Right, exactly.
Right, yes. And whenever people, you know, publish a differentially private algorithm, at least in my literature, in our field, it's always accompanied by bounds on that tell you something about the distribution of the errors. So
for the Laplace noisy.
And hang on, when I had that discussion about what did this theorem mean for the GWAS, this is exactly what I was talking about. So if you're looking for things like what fraction of the people, you know, have a C versus a T, you need your errors to be small enough. And we get something that makes some sense up to but not after, almost up to n but not after that. And then we switch to the more relaxed definition and so on.
Right, and I can see when you're doing the noising version,
Yes.
that the idea of utility is pretty
Yes.
easy to get a hold of.
Right.
But that's, noising is not the only.
You're right. And so, for example, suppose you're choosing, you have a differentially private algorithm to, I cannot use a voting example given what happened, I cannot, to choose from a discrete set of some sort, all right, to choose the most representative tree of something or others, all right? So then what you do is you associate with each tree, you have a utility function which takes as input a possible output and your current data set and gives you a measure of utility. And it should be a meaningful measure, obviously. And you use that in making your selection, and then afterward you can prove theorems about how likely is it that the utility will be no worse than blah. And you get a bunch of confidence intervals that way.
So it'll be specific to a given utility function.
That would be one,
Yeah.
in this instantiation, that's what it would be.
Very good.
Yeah.
Thank you.
Yes.
I just want to follow up on Jane's question, because you mentioned about finding that some aspect with your independent sample would not be representative of the population. But if you have enough characteristics, just by carrying out we know by many tests, that we know the high probability one of the characteristics will not be, the CI won't cover it.
Right.
So I'd like you to clarify that.
Good. So I think the really more clean way of saying it is that if you use differential privacy, then your repeated access to the data set does not help you beyond what you could do if you were blind guessing. Something like that. So blind guessing eventually lets you land on something, and eventually in the differentially private interaction you could land on something, but it shouldn't be faster. Okay?
Right, you can't get around Alice's restaurant theorem, but that's your bound on the number of queries. And you won't.
Alice's restaurant there?
Well, that if you have high dimensional data, there's
Yeah.
anything you want in some projection.
Right.
Mark? Mark, yeah.
I had about 25 questions, but I've just been mulling over which one I would pick to ask you. So, what would Helen Nissenbaum's motivation for participating in your survey be, given that her presence or absence in the survey does not affect the outcome of any query?
Well, it has a small outcome on the query. And so what you hope is that by making it safe for people to participate, you will get more people to participate. And if your data set is large enough, then you can get very accurate answers, even while maintaining differential privacy. So for example, in the case of the counting queries, the noise that you're adding depends not on the size of the database, but on the counting query. And I mean on the sensitivity of the counting query, which is 1, and the privacy loss, which is epsilon. So you're adding noise that looks like 1 over epsilon. That may be relatively large when the data set is small, but if the data set is very large, the noise that you're adding for privacy is very tiny. So we want to encourage a lot of people to join. And so the answer would be basically altruism. She might be interested to know whether smoking causes cancer or other health things. But we do want to make it safe. Does that answer?
Oh, okay.
Half.
Well,
I'm
perhaps
sorry.
the other half, and it should be
I'll have the
over a
other
glass
half.
of wine. We'll perhaps take one more question from Natalie.
I was just wondering if give a lot of examples in the counting queries. So say that the proportion of people in like Britney Spears. What about the zeros? Do you have to protect the zeros as well?
So you mean if the answer is
There's
0?
nobody who likes Britney Spears.
Yes, right. Okay, so what would happen if you used a differentially private algorithm in the Laplace mechanism, and the true answer is 0? What will happen is you'll get a negative number. So, and in fact, you would be almost as likely to get that same negative number if the answer is 1. That's what it means to be differentially private. So what it means is that the person the analyst who is interpreting the answers has to understand what the noise looks like and understand the distribution on the noise, not the actual noise value. And understand that a negative number probably means that the actual number of fans is small.
But you would protect that, even though there was nobody in the data set that.
Well, again, what if there might have been, so there might have been nobody who preferred Kobe's slides, thank you, and then Helen stops reading her mail, and now we find out that there is somebody. So yes, we would still protect it because we have to protect Helen should she join later. Yeah.
Okay, well, perhaps we should continue this conversation over wine, to which everybody is invited. So once more, it's really wonderful lecture. Thank you.